Chapter 26, Geometrical Optics. Here is the overview of Chapter 26. We will first talk about the reflection of light and then talk about how images are formed via the reflection of light with a plane mirror. We will then talk about spherical mirrors, move on to ray tracing and the mirror equation, which helps us determine where images will be placed with respect to objects. Then we will talk about the refraction of light, show some ray tracing for lenses, the thin lens equation, and finally we will talk about dispersion and how rainbows form. As we discussed in the previous chapter, light is an electromagnetic wave that will travel in a direction away from the source. We can make an analogy with a stone that is dropped in a pond. The source is the location where the stone is dropped, and when it is dropped, there will be circular waves which emanate from that point. We can see in this example that the circular waves have wave fronts, and the direction of the wave fronts is denoted by the rays, which tell us exactly in which direction the waves will propagate. We can also make the same analogy with light itself. The law of reflection tells us the direction of a reflected light ray upon it hitting a surface. If the incident wave has an angle theta I with respect to the normal of the surface, then the reflected wave will have an angle theta r, and this reflected angle is exactly equal to the incident angle. We characterize reflection in two ways, and for each way the law of reflection still applies. The first way is specular reflection, and this is reflection from a very smooth surface. A mirror is an example. Here we have three incident rays that reflect off the surface, and they all travel in the same direction after they have reflected. The second type is diffuse reflection. An example of this would be reflection from a piece of wood or a carpet. Here the surface is not smooth, and the rays that are reflected do not travel in the same direction after they hit the surface. They travel in random directions. They still obey the law of reflection, and the reason that they travel in different directions is that the normal will point in different directions depending on where you are on the surface. This is not the case for specular reflection, where the normal will always point upwards. Now we will move on to how images are formed, and the simplest example is an image formed from a plane mirror. Firstly, let's define what an image is. An image is a geometrical object where light appears to originate from. Here we have an example where an object, which is a vase, is placed in front of a mirror. Light will leave the object. It will then reflect in a specular manner from the mirror, and the rays of light will then enter the eye. All these rays will obey the law of refraction, and what happens is when the eye looks into the mirror, it thinks that the object is at position P dash, not P. The reason for this is the eye interprets light as travelling in a straight line, and because of that, it would assume that the vase, which is at position P, is really at position P dash. Regarding the properties of the image at P dash, the first property is the mirror image will be upright, but it will appear reversed right to left. One can see an example of this when one looks at the mirror with some text on their clothing. You will see that the text appears to be going in the wrong direction, and this is the reason why sometimes ambulances will have their own text reversed, so when one looks in the mirror, the text of the ambulance will appear to be written in the right direction. The second property is that the mirror image for a plane mirror will appear to be at the same distance behind the mirror as the object is in front of the mirror. The final property is the size of the image will be exactly the same as the size of the object. Here in this diagram, DO represents the distance of the object and DI represents the distance of the image. We can also see some angles that happen to be equivalent depending on where they are measured from. Another interesting property regarding plane mirrors is if we arrange them in a corner as shown, a light that is incident and it gets reflected several times to make a reflected ray, that reflected ray will be parallel to the incident ray no matter what the incident angle is upon the first reflection. A spherical mirror has the shape of a section of a sphere that has been cut out of the sphere. If the reflecting surface is on the outside, then we refer to this as a convex mirror. On the other hand, if the reflecting surface is on the inside, we refer to this as a concave mirror. Spherical mirrors will have a principal axis and a center of curvature, which is essentially the center of the sphere. We can see two instances here where we have a concave mirror on the left as the reflecting surface is inward, and a convex mirror on the right as the reflecting surface is outward. In this slide we show what happens when parallel rays hit a convex mirror and are reflected back. The law of reflection applies. We can see one example where we have a parallel ray at the top and the reflected ray will have the same angle with respect to the normal as the incident parallel ray. With a convex mirror, the reflected rays appear to come from the focal point, but they don't actually originate there. The focal point, which is denoted by F, is closer to the mirror than the center of curvature, which is denoted by C. Here we have the case for a concave mirror. We have parallel rays that hit the mirror, and these actually meet at the focal point, which is denoted by F, and after the focal point they will start to diverge. Again, the focal point is closer to the mirror than the radius of curvature, which is denoted by C, and we can see an example of the law of reflection happening where the top parallel ray hits the mirror and is reflected towards the focal point. The focal length for a concave mirror, which is the length that it takes for parallel rays which are reflected to converge at the focal point, is equal to half the radius of curvature of the mirror itself. For a convex mirror, the reflected rays do not converge, they diverge, but they appear to come from the focal point. And in this case, the focal length will be minus half the radius of curvature of the mirror. We assign a negative focal length for a convex mirror and a positive focal length for a concave mirror. And the reasons for this will become obvious later. For a spherical concave mirror, it actually turns out that the rays that hit the mirror very close to the principal axis do not converge at the focal point. This means that any images we would like to form from this mirror will be blurred, and we refer to this as a spherical aberration. This can be remedied by using what's called a parabolic mirror instead. The equation for the curvature follows a parabola rather than a circle. It actually turns out that the Hubble Space Telescope, which was the first telescope that was launched into space, suffered from these spherical aberrations. There needed to be extra missions to fix this, so the aberrations didn't occur. The missions were referred to as corrective optics, and they were indeed successful. Now we will discuss ray tracing. Ray tracing helps us determine the nature of an image formed from an object, whether it's upright or inverted, and it also tells us where exactly the image will form in relation to the mirror. There are three rays that we use for ray tracing. The first is the P-ray. This starts off parallel, then is reflected from the mirror and goes via the focal point. The second ray is the F-ray. This travels through the focal point, and when it's reflected, it moves in a parallel direction in relation to the principal axis. The third ray is the C-ray. This travels through the center of curvature, hits the mirror, and then comes back in exactly the same path that it traveled to before it hit the mirror. Here is an example of ray tracing used when we have a convex mirror. We have the P-ray, C-ray, and F-ray, and when they reflect from the mirror, they don't actually converge to form what we refer to as a real image. What they do form is a virtual image, which is exactly the same type of image that a plane mirror forms, and we calculate its position by projecting back the reflected rays and seeing where they cross. Here we can see that the reflected parallel ray is going to the top left-hand corner of the slide. If we then project back, we get the dashed line, and we can then do the same for the C-ray and the F-ray, and all of these lines that are projected back, they will cross at a particular point, and this is where the image occurs. We can also see that the image will be smaller than the object, and it sits between the mirror and the focal point. We can also carry out ray tracing for a concave mirror, and in this instance we only need the P and F rays to determine the image size and location. On the left, we place the object behind the radius of curvature, and we find the image will form at the point where the reflected P-ray and the reflected F-ray will cross. In this instance, the image will be smaller than the object and it will be inverted. On the right, the object is moved between the radius of curvature and the focal point. Again, we can look at the reflected P and F rays and they cross behind the object. This gives us an image that's actually greater than the object and it's still inverted. In addition to ray tracing, we can use the mirror equation to determine the position of the image. Here, DO is the distance the object is away from the mirror, DI is the distance the image is away from the mirror, and F is the focal length. The mirror equation states that 1 over DO plus 1 over DI will be equal to 1 over F, the focal length. The object can be moved in a variety of positions and this will often lead to different image types. For a convex mirror, it turns out that wherever the object is, one always gets a virtual image and the image is always upright. For a concave mirror, when the object is behind the radius of curvature, the image will be inverted and its size will be reduced relative to the object and it will be a real image. And real images occur when the reflected rays actually cross. When we put the object at the radius of curvature, we still get an inverted image and its size is the same as the object and it's still real. We can then push it a bit further between the focal length and the radius of curvature. In this case, the image will still be inverted, its size will actually be bigger than the object, and it will remain real. We can keep going, and when we put it inside the focal length, something different happens. The image formed will be upright rather than inverted. The size will be very big, and it will be virtual, and it's virtual because the reflected rays, if you put the object close enough, do not actually converge, but one can project the reflected rays back with these dashed lines and we find that the projected lines do converge and this gives us a virtual image. We can also determine the magnification, which is denoted by M. This will equal the height of an image divided by the height of the object. When the image is bigger than the object, this is bigger than 1. When the image is smaller than the object, this is smaller than 1. The magnification is also related to the distance of the image and the object, and it's equal to minus the image distance divided by the object distance. This tells us that when the image distance is large, the size of the image will be big, and vice versa. When using either the thin lens equation or the equation for magnification, one has to really ensure that the correct signs are used for the focal length, the image distance, object distance, image height, and object height. The focal length for a concave mirror is always positive, and for a convex mirror is always negative. When the magnification is positive, we have an upright image. When it is negative, we have an inverted image. The image distance for real images is always positive, and for virtual images, this is always negative. For example, a convex mirror will always produce a virtual image, so for a convex mirror, always make sure that the image distance used is negative. In terms of the object distance, almost always for this chapter, this will be positive. There are some situations where it might be negative, but that is not relevant for the questions in this chapter. Now we will discuss the refraction of light, which is essentially the bending of light when it moves from one media to another. It turns out that light itself will move at different speeds in different media, and as mentioned before, when this happens, it turns out that these differences in the speeds will cause the light to bend. The speed of light in a medium is often referred to in terms of the index of refraction, and that is defined as the velocity of light in a particular medium, which is v, divided by the velocity of light in the vacuum, which is c. In this equation, we rearrange it so the velocity of light in a medium is equal to the velocity of light in a vacuum divided by the index of refraction. So essentially the index of refraction, which has to be above 1, is telling us how much light is slowed down within a particular medium. It turns out that different materials which allow light to pass through it have different indices of refraction. Diamond has the highest at a value of 2.4, which means light is slowed down by a factor of 2.4 when it travels through diamond. There are other materials such as glass, ice, and some liquids, and indeed gases, and in the order that we see, all of these will cause light to slow down. As a general rule, solids will tend to make light slow down more than liquids, and liquids more than gases. Snell's law tells us how much light is indeed bent when it goes from one medium and passes to another. N1 is the index of refraction of the first medium. We multiply that by sine theta 1, where theta 1 is the incident angle with respect to the normal, and that will equal N2, which is the index of refraction of the second medium, times sine theta 2, where theta 2 is the angle between the refracted ray and the normal. We can see in this example that the higher the indice of refraction of the second medium, N2, the more light will bend. In this example, glass has a higher index of refraction compared to water, and we can see that the light is bent more because the angle with respect to the normal is smaller. If light wasn't bent at all, then that angle would be 60 degrees. Refraction can make objects immersed in water appear broken. We have an example on the left where we place a pencil in water. The rays from the pencil travel out of the water towards the eye, but they are bent in the process, and the eye assumes that the rays are not bent and essentially misplaces the position of the pencil to give an apparent position, and this causes the illusion of the bending of the pencil. A second example is a mirage. In this example, the ground is heated to a higher temperature than the air, and the air just above the ground will have a higher temperature than the air further up. Because of these differing temperatures of the air, one has essentially two different indices of refraction, and this can cause light to bend. When this happens, the palm tree will appear that it's coming from below the ground, which creates this mirror image effect that we often see on roadways that are very hot. Here we will see what happens when light passes through one medium with a high index of refraction and tries to escape to another with a lower index of refraction. The medium with a high index of refraction is referred to 1, and with a low it's referred to 2. In A, we have a very shallow angle with respect to the normal. Some of the light will be reflected, and the light that is refracted will make an angle of theta 2 with respect to the normal. Here it will be bent away from the normal relative to the incident light. We can then increase this angle with respect to the normal. For the incident light, we make theta 1 bigger. We still find some of the light is refracted, and the refracted light is bent even more so relative to the first example. The reflected light will have the same angle of reflection as the angle of incidence, which comes from the law of refraction. At some point, we can increase theta 1 to a point where the refracted light passes at 90 degrees with respect to the normal. We still have some light that is reflected, which is shown by theta 1, and then if we increase the angle even more to get to the example of D, we find that none of the light is indeed refracted and all of it is reflected. This we refer to as total internal reflection. If one tries to calculate the refracted angle from Snell's law, one gets an imaginary number. We refer to the incident angle that corresponds to a refracted angle of 90 degrees as the critical angle theta c. Here we have two devices that use total internal reflection, a pair of binoculars on the left and some fibre optic cable which is used to carry information such as internet traffic on the right. When travelling from a low index of refraction to a high index of refraction, there is an angle referred to as Brewster's angle, and in this case the light that is reflected is totally polarized. The light that is refracted is not polarized. We can calculate Brewster's angle pretty straightforwardly. The tan of Brewster's angle will equal the index of refraction of the second material divided by the index of refraction of the first material. Now moving on to ray tracing for lenses. Lenses are also able to form images from objects that can be a different size to the object and can also be inverted. They are used to focus light in the same way as mirrors are used to focus light, and there are two types of lenses. The first is a convex lens, and for the purpose of this chapter we'll focus on the double convex lens. And the second type is a concave lens, and again for this chapter we will focus on the double concave lens. We can think of a convex lens as consisting of a series of prisms. Here is how the lens works. We have some parallel rays that hit the lens and they converge to a particular point, which is the focal point. The distance between the focal point and the lens itself is referred to the focal length, exactly in the same way as we calculate the focal length for mirrors. A concave lens can also be thought in the same way, and for a concave lens, what happens is parallel light will hit the lens and the refracted rays diverge. However, one can draw these dashed lines which shows a projection of the refracted rays, and it turns out that these dashed lines will meet at a particular point which we refer to as the focal point. Again, the distance between the focal point and the lens is known as the focal length. We can also carry out ray tracing for lenses just in the same way as we did for mirrors. The P-ray will start off as parallel as it leaves the object, and then it will be bent when it hits the lens, and the refracted ray will go through the focal point F. The M-ray, where M stands for middle point, will travel through the middle of the lens, and this is not actually bent in the process. The final ray is the F-ray. This goes through the focal point first, and when this is refracted, it will travel in a parallel direction with respect to the principal axis. Here we have an example of an image formed by a concave lens. We draw out the P, F and M rays from the object, and we find that when they are refracted, their projected rays can be used to determine the position of the image. This will happen where all the dashed lines essentially cross, and we can determine both the distance and the size of the image using this method. Just like for a concave mirror, a convex lens will form different images depending on where the object is with respect to the focal point. On the left, the object is in front of the focal point. The image formed will be real since the refracted rays converge at a particular point, and the image will be inverted. When we place the object in front of the focal point, the refracted rays diverge. If they diverge, they create a virtual image. This can be calculated by projecting back with the dashed lines to see where these projected rays cross, and that will be where the location of the image is. The image in this case will be both upright and it will be bigger than the object. In addition to ray tracing, we can use an equation that is exactly the same as the mirror equation. For this case, we refer to it as the thin lens equation, and that tells us that 1 over the image distance plus 1 over the object distance will equal 1 over the focal length. The magnification is defined in the same way, and this will be equal to minus the image distance divided by the object distance. Again, for the lenses, one has to take the signs very seriously. For a convex lens, the focal length will be positive. For a concave lens, the focal length will be negative. Just as for mirrors, the magnification is positive if the image is upright, and it is negative if the image is inverted. The image distance will be positive if we have a real image, and a real image will correspond to where the rays actually converge. The image distance will be negative for a virtual image, which is on the same side of the lens as the object, and in this case the refracted rays don't converge, but they can be projected back to a particular point. For the object distance, for the purpose of this chapter, this will be positive for all situations. The final thing that we will discuss is dispersion and how dispersion forms rainbows. It turns out that the index of refraction depends on the frequency of the light itself. The higher the frequency, the higher the index of refraction. Here we have an example on the right. The red light has a lower frequency than the blue light, and because of this, the prism will have a lower index of refraction, which means that the red light will be bent less than the blue light. This means that light of all colours, when it hits the prism here, will be spread out. And this is what we refer to as dispersion. In this example, we will show what happens when light hits a raindrop. It enters as white light. It will then be refracted, and the different colours, red and violet, will be bent in different ways. These two colours will then be reflected, and then when they leave the raindrop and enter the air again, they will again be bent in different ways. If we measure the angle between the parallel line and the violet light, this will be 40 degrees, and the red light, this will be 42 degrees. To see a rainbow, the sunlight will have to be coming from behind a particular person. It will then hit the raindrop and then get reflected in a way where the light disperses, and these different colours that we see in the rainbow arise from this dispersion, which comes from the fact that different colours get bent in different ways.